This is SpaceTime Series 21, Episode 100. Coming up on SpaceTime, the largest black hole collision ever observed, the Voyager 2 spacecraft enters interstellar space, and Virgin Galactic reaching for the stars. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered the biggest and most distant black hole collision ever observed. The massive event was one of 4 new black hole mergers detected as scientists sifted through the huge archival data streams generated by the first 2 observing runs of the LIGO Gravitational Wave Observatory. The findings, reported in the journal PRX, indicate the event, catalogued as GW170729, occurred during LIGO's second observing run on the 29th of July 2017. It was the most massive and distant gravitational wave source ever observed. The merger, some 5 billion light-years away, involved the collision or coalescence of 2 stellar mass black holes, one about 50.6 times the mass of the Sun and the other around 34.3 solar masses. They merged to form a black hole of some 80.3 solar masses, in the process releasing around 5 times the mass of our Sun in pure gravitational energy. Scientists also found the event involved black holes spinning faster than any other merger so far. The other 3 newly detected black hole mergers ranged from 2.5 to 3.9 billion light-years in distance, resulting in the formation of new merged black holes between 56.4 and 65.6 solar masses. The 4 new discoveries mean that in just 13 months of gravitational wave observations, no less than 10 stellar mass black hole binary mergers and 1 binary neutron star merger have now been detected. That's almost 1 a month, and we're only just starting. The neutron star merger was especially exciting as it was observable not just using gravitational wave observations, but also conventional optical, radio, infrared, X-ray, gamma-ray, and ultraviolet telescopes. And it may have resulted in the birth of a new black hole. LIGO, the Laser Interferometer Gravitational Wave Observatory, comprises 2 identical facilities located in Livingston, Louisiana and Hanford, Washington State. Each LIGO observatory fires lasers into a beam splitter, which then shoots the beams along 2 perpendicular 4-kilometre-long tunnels equipped with mirrors at the far ends. The reflected laser light is then sent back to a detector, where eventually the 2 beams should theoretically recombine, provide some sort of interference pattern. As a gravitational wave, generated by a moving mass, say merging black holes, passes through the cosmos, it causes the very fabric of space-time itself to stretch and compress ever so slightly, by just a fraction of the diameter of a proton. When a gravitational wave passes through the LIGO detector, local space-time, including the 2 beamlines, reflected lasers, are each alternatively stretched and compressed ever so slightly, leaving them out of phase, the telltale signature of a gravitational wave event. Using multiple gravitational wave detectors allows scientists to determine the direction of the wave source, and the addition of a 3rd detector called Virgo, located near Pisa in northern Italy, has further improved gravitational wave detections. And a 4th gravitational wave detector, originally offered to Australia but rejected by the then Gillard Labor government, is now being built in India. From September the 12th, 2015, through to January the 19th, 2016, during the first LIGO observing run since undergoing upgrades in the program called Advanced LIGO, gravitational waves from 3 binary black hole mergers were detected. The second observing run, which lasted from November the 30th, 2016 through to August the 25th, 2017, yielded a binary neutron star merger and 7 additional binary black hole mergers, including the 4 new gravitational wave events. It took science a century to confirm Albert Einstein's prediction for the existence of gravitational waves. And now, in less than 3 years, gravitational wave detections have provided direct evidence for the existence of black holes, another prediction of Einstein, as well as binary black hole and neutron star collisions. The LIGO detectors are now undergoing another upgrade to further improve their performance. One of those working on the project and one of the authors of this study, Professor Susan Scott from the Australian National University, says the new window on the universe being offered by gravitational wave observations has revealed just how frequent these mergers are. Scott says these detections of black hole collisions greatly improve science's understanding of how many black hole binary systems there are in the universe, as well as the range of their masses and how fast black holes spin during a merger.
What we've done is, after the finish of the two observing runs of LIGO and Virgo, 01 and 02, we've re-cleaned the data and we've recalibrated it very carefully. And in addition, we've refined our searches, for instance, enlarging the parameter space over which we search. And with that combination of things, it became a good thing to do to actually go back and analyse all the data from the two observing runs. And with the increased sensitivity, we managed to uncover 4 amazing new binary black hole inspirals and mergers. So we were extremely excited about that. We had 5 announced previously, and that was the other good thing about going back and reanalyzing the data. We were able to further refine the significance of our earlier detections and announcements and better estimate their parameters. And in so doing, this October event in 2015, on the 12th of October, was elevated to a gravitational wave detection. So the 5 became 6. And then we've added 4 more.
It's all looking good for gravitational wave detection, and LIGO and Virgo is a new window on the universe.
Well, that's absolutely right. I mean, we're due to start our 3rd observing run on April Fool's Day next year. Remarkably. That's another thing, that with the additional detections we've unearthed from our first 2 runs, we've been able to get a better estimate of the probable merger rates, the inferred merger rate from the data and detections we've got. And this is really giving us a lot of confidence for the 3rd observing run, that we think it's possible we could have at least a few binary black hole detections per month, maybe 1 a week, and that over the course of the year of the 3rd observing run, we may get 1 to 10 binary neutron star mergers and possibly up to 1 per month. And of course, we're still after our elusive target of a binary of a black hole and a neutron star.
1 a week certainly looks feasible based on that small window we've got there.
That's right. That's what our rates are suggesting. And for the days of data that we were running in coincidence, we actually averaged something like 1 detection per 15 days, even with the sensitivity that our detectors were at during those 2 observing runs.
Tell me about these new discoveries.
Of our 10 binary black hole mergers, our lightest component black holes are around 7-point-something solar masses. But in one of these 4 new events that we've announced, one of them is actually our biggest binary black hole system so far, and its larger mass was something like 50 solar masses, which is, really, really big. And that signal came in on the 29th of July 2017. And as a result of this increased number of detections, we get a better estimate of the sort of masses that these binary black hole components will and can have. The biggest black hole collision which we've detected so far, which was one of the new ones, is also the furthest of our detections, so it breaks 2 of our records. And it's also the detection which gives us the strongest indication of some kind of spin of the component black holes. And we're not able at the moment, with the sensitivity we have, to measure that very well. But this is tantalizing because it's a departure from the other observations.
This is showing that we're getting closer and closer to that intermediate mass black hole type threshold that astronomers have been looking at for a long time now, aren't we?
That's right.
Depending on what your definition of intermediate is, I guess.
Well, that's right. I mean, we call it our stellar graveyard. If we plot our binary black hole detections, they do fit within the known spectrum of black holes that have been observed by not only gravitational waves but other means as well. And there are 2 kind of gaps, and one is between the neutron star mass range and the lightest component black hole, so around about 2 to 5 solar masses. And then there's another gap up above the, say, 70 solar mass range at the top end of the spectrum. And there are theories about why each of those can occur, but it's great that by getting new detections, we can actually probe those mass gaps better than has previously been done.
And LIGO's being upgraded right now, isn't it, in time for its next run?
Yes. So we've been offline for quite a while, and that's because we're doing amazing things to our detectors to make them more sensitive so we can see more things and see out further into space. So in particular, we've implemented a few key things like squeezed light injection, which will help with the shot noise of the lasers. And also we've dealt with issues to do with scattered light and jitter mitigation. We've also been improving the lasers to help with shot noise again, and various other little problems that have, the detectors are really getting on by now because we started building them in the early 90s. So that it's like a house or something, things need to be maintained and fixed over such a long period. So we've had to do a certain amount of that as well. And all these things are happening, and the combination is that we expect to have better sensitivity when we go online in April next year.
And not only do you have the 2 LIGO detectors, there's also Virgo in Italy, and very soon there'll be one in India as well. They're working to develop that now.
Yes, well, Virgo joined for the last month of the second observing run, and although it was at a significantly lower sensitivity than the LIGO detectors, it tremendously helped that the observations we got in the last month in terms of localizing those events to a smaller region of the sky. And Virgo is also being upgraded, and they're going to implement things that we have in LIGO like signal recycling and so on. And they will be joining the third observing run. LIGO India hasn't really been constructed as yet. And when you construct an interferometer of this size, it takes a long time, as we know well. And so they're not going to be online anytime soon, actually, certainly not for the third observing run.
As I'm speaking to you, you're in Western Australia right now in Perth, and one of the pioneers of gravitational wave observatories in Australia is some of the research being done at Gingin. How's that going?
Well, it's going very well. Gingin is a very multifaceted complex where we do a lot of outreach for school students and the public to see what gravitational wave work is all about. So it has all that side of it, but there's also a very important research facility there, which we've had now for a couple of decades, and we have developed components and technology for the LIGO instruments, but also we really have had a vision of having our own detector here in Australia, and this is something we're still working towards, and we're keen on the idea now of having a high-frequency gravitational wave detector, which could really help probe certain parts of the frequency range which we can't really probe easily with the current detectors, and that would apply to things to do with the detailed structure of, say, a neutron star collision, the tidal aspects and so on. And we feel that that could be a really important niche that Australia could fill.
Difficult to explain it to people, but you guys are really looking for the stretching of space-time, and you've got to take into account quantum fluctuations in the fabric of space-time itself. This is an incredibly delicate thing you're doing.
Yes, the one thing I'd say about gravitational wave detection, and therefore the ensuing gravitational wave astronomy that we have now, is that it is mind-boggling the complexity of all the components of our system, our detectors, our technology, but not only that, the intricacy of firstly generating potential waveforms that we can detect and using those to probe the astrophysics of the sources that they come from. If you look at the whole project in its entirety, it is amazingly complex and intricate.
You're looking for things that are smaller than the diamond of a proton, aren't you?
That's right. And I think that's one of the things that we commonly say about our detectors, that gravitational wave will affect space between here and, say, Andromeda by the width of a human hair. That's the incredible level of sensitivity that we've needed to be able to detect these phenomenally faint gravitational waves.
That's Professor Susan Scott from the Australian National University. And this is Space Time. I'm Stuart Gary. For only the second time in history, a spacecraft has travelled beyond our solar system and entered interstellar space. NASA's Voyager 2 spacecraft has exited the heliosphere, the protective bubble of particles and magnetic fields created by the Sun, and in the process entered the space between the stars. Mission managers, comparing data from different instruments aboard the probe, have concluded that Voyager 2 crossed the outer edge of the heliosphere on November 5th. This boundary, called the heliopause, is where the tenuous hot solar wind meets the cold, dense interstellar medium. The spacecraft's twin, Voyager 1, crossed this very same boundary back in 2012 at a distance of 121 astronomical units from the Sun, although it took over a year for scientists to realise it happened. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. And unlike Voyager 1, Voyager 2 has more instruments that are still working, thereby providing scientists with first-of-its-kind observations of the nature of this little explored region. Voyager 2 is now slightly more than 18 billion kilometres or 120 astronomical units from Earth. And mission managers are continuing to communicate with the probe as it enters the new phase of its journey. But it's painstakingly slow. You see, information, even moving at the speed of light, still takes some 16.5 hours to travel from the spacecraft to Earth. The most compelling evidence for Voyager 2's exit from the heliosphere comes from its onboard plasma science experiment, an instrument which had stopped working on Voyager 1 back in 1980, long before that probe crossed the heliopause. Until recently, all the space around Voyager 2 had been filled predominantly with plasma flowing out from our Sun. This outflow, known as the solar wind, creates a bubble, known as the heliosphere, that envelops all the planets in our solar system. The plasma science experiment uses the electrical current of this plasma to detect the speed, density, temperature, pressure and flux of the solar wind. And on November the 5th, it observed a sudden steep decline in the speed of solar wind particles. And since that date, the plasma instruments observed no solar wind flow in the environment around Voyager 2, which makes mission scientists confident the probe has left the heliosphere. Even though Voyager 1 crossed the heliopause back in 2012, it did so in a different place and at a different time, and without the plasma science experiment data. So scientists are seeing things now that no one's seen before. In addition to the plasma data, Voyager's science team have also seen evidence from 3 other onboard instruments: the cosmic ray subsystem, the low-energy charged particle instrument, and the magnetometer. All are consistent with the conclusion that Voyager 2 has indeed crossed the heliopause. Voyager 2 mission managers are now eager to study the data from these other instruments to get a clearer picture of the environment through which the spacecraft is now travelling. Voyager project scientist Ed Stone from Caltech says there's still a lot to learn about the region of interstellar space immediately beyond the heliopause. Together, the 2 Voyager probes are providing a detailed glimpse of how our heliosphere interacts with the constant interstellar wind flowing from the rest of the galaxy. The Voyager observations also complement data from NASA's Interstellar Boundary Explorer IBEX mission, which is remotely sensing this boundary region. NASA's also preparing an additional mission, the upcoming IMAP Interstellar Mapping and Acceleration Probe, which will launch in 2024 to capitalize on Voyager's observations. Now, while we're saying the probes have left the heliosphere and therefore left the solar system, technically Voyager 1 and Voyager 2 have not yet really left the solar system completely. See, right now, the boundary of our solar system is considered to be beyond the outer edge of the Oort cloud, a collection of comets and icy debris following the Sun and solar system through the galaxy under the Sun's gravitational influence. The exact size of this spherical Oort cloud isn't really known all that precisely. In fact, we don't know if it's really there. But it's estimated to begin somewhere well beyond the Kuiper Belt, about 1,000 astronomical units from the Sun, and then extend out to maybe 100,000 astronomical units. Now, if all that's right, it'll take Voyager 2 some 300 years to reach the inner edge of the Oort cloud, and possibly as much as 30,000 years to fly beyond it. And that could be problematic. You see, the Voyager probes are powered using heat from the decay of radioactive material contained in a device called a radioisotope thermal generator, or RTG. The power output of the RTG diminishes by about 4 watts per year, which means that various parts of the Voyagers, including the cameras on both spacecraft, have been turned off to conserve power. And as the RTGs continue to power down, more and more systems will need to be shut down. Voyager 2 was launched back in 1977, 16 days before its twin Voyager 1. The 2 spacecraft were on a mission described as a grand tour of the outer solar system, including close-up studies of the gas giants Jupiter and Saturn. Voyager 1 would then study the Saturnian moon Titan in detail, Titan being considered an analogue for the early primordial Earth. After visiting Titan, the spacecraft will continue travelling in a, well, I guess you'd call it a northerly direction out of our solar system, travelling above the plane of the ecliptic, the imaginary disk surrounding the Sun around which all the planets orbit. But orbital mechanics meant the 2 outermost giant planets, the ice giants Uranus and Neptune, would allow Voyager 2 to use the gravity assist of Saturn to slingshot itself to Uranus. and then using the gravity assist of Uranus to slingshot itself further out to Neptune. After exploring these two ice giants, Voyager 2 would then explore the Neptunian moon Triton, thought to be a captured Kuiper Belt object, before it too would exit the solar system. But instead of heading north like Voyager 1, it would head south below the plane of the ecliptic. Now, 41 years later, Voyager 2 has finally left the solar system. The story of the Voyager spacecraft and their discoveries hasn't just impacted on generations of current and future scientists and engineers, but also Earth's culture, including film, art and music. Each spacecraft also carries a golden record containing sounds of Earth as well as pictures and messages. And there's a plaque on the side of each spacecraft as well, showing exactly where Earth is in the solar system in relation to various pulsars and what human Earthlings look like. And since these spacecraft could last for billions of years as they continue their interstellar journey, these could end up being the only traces of the existence of human civilization. Voyager's mission controllers communicate with the spacecraft using NASA's Deep Space Network, a global system for sending and retrieving telemetry from interplanetary missions. The network consists of 3 clusters of antennas located at Goldstone in California, Madrid in Spain, and at Tidbinbilla near Canberra in Australia. On November the 8th, the CSIRO's Parkes Radio Telescope joined NASA's Canberra Deep Space Communications Complex to help in efforts to maintain communications with Voyager 2. The Parkes dish will help scientists glean a clearer picture of the environment through which Voyager 2 is now travelling. You see, because of Voyager 2's location and distance from Earth, the Deep Space Canberra Tracking Station and the Parkes Telescope are the only facilities on the planet capable of having direct contact with the spacecraft. Voyager 2 isn't able to record its data on board. It transmits it directly to instruments back on Earth, making it essential to receive as much of this vital data as possible. To collect this data, the 64-metre Parkes dish will be tracking the Voyager 2 spacecraft for 11 hours a day while the spacecraft is observable from Parkes. As well as that, NASA's Deep Space Canberra Tracking Station's 70-metre dish, DSS-43, will also track Voyager 2 for a number of hours, both before and after Parkes, thereby expanding the available observational time. Glenn Nagel from NASA's Canberra Tracking Station says gathering this historic data will be a joint effort.
This is a mission that we've been tracking here in Canberra through the Deep Space Network for 41 years, since the mission left in 1977 throughout its planetary encounters with Jupiter, Saturn, Uranus, Neptune, and now on the interstellar mission. And it's wonderful that the data that we've been receiving over the last few months, which has given indications to the science team that it may have been approaching the heliopause boundary, that it eventually did cross it on the 5th of November. Of course, now the mission wants to get more information because unlike Voyager 1, when it crossed the heliopause in 2012, it didn't have the instrumentation on board still operating to really learn enough about that environment. Voyager 2 does. So this is why NASA has come to us through the CSIRO to engage the Parkes Radio Telescope so that we can use our 2 dishes combined together as a single force to collect maximum information from Voyager 2.
And of course, Voyager 2 is heading into a different direction to Voyager 1. That's because, unlike Voyager 1, which visited Jupiter and Saturn, Voyager 2 continued on the grand tour, also visiting Uranus and Neptune.
So yes, its flight path made it possible to take advantage of a special alignment of the planets that only happens about 176 years in span, and to be able to use the gravitational assist of Saturn to slingshot the spacecraft Voyager 2 out to Uranus and then Neptune, the only spacecraft to ever visit those worlds. And as you mentioned, yes, Voyager 1 only went to Jupiter and Saturn. Its gravity kicked, then slingshotted it sort of northward. And then Voyager 2, it continued on and made its encounter with Neptune in 1989, and then using gravitational slingshot to send it southward out of the ecliptic plane. So they're generally heading off in the same direction, but north and south of each other.
The other big deal here is that, unlike Voyager 1, this time we knew it was coming. We knew this move from interplanetary to interstellar space was on its way. With Voyager 1, we had an idea it was going to happen, but we're about a year late before we could determine for sure that it did happen.
Yes, and there was a lot of confusion with Voyager 1's data because there were times when they thought it had reached the heliopause boundary and into interstellar space, and then because of just fluctuations in the actual heliosphere boundary, it was travelling in and out of that. So it eventually, yes, it took them about a year to eventually determine that absolutely, with the limited instrumentation they had on board, they could determine it had reached interstellar space. Of course, all the things we learnt from Voyager 1 gave the scientists the actual capability to say, these are the signs we must look for. And so we're much better placed with Voyager 2 and, of course, with its operational instrumentation on board to measure that approach and then eventually the exit. Important thing about Voyager 2, though, while it had those instruments to measure the environment, its onboard recorder was no longer operational. So Voyager 2 actually sends back its information continuously. So without antennas here in the Southern Hemisphere, both the Deep Space Tracking Station in Canberra and with the use of the Parkes Radio Telescope, we wouldn't be able to collect the maximum volume of that data, which would otherwise just be lost to the universe.
Pretty significant move then.
Very important, and it just shows the great collaboration that has gone on between our National Science Agency, CSIRO, and NASA, a partnership that's lasted over 50 years. And it's great that we can bring in Parkes to once again support Voyager, which it has helped in the past when we've had some of the most distant encounters with Uranus and Neptune.
18 billion kilometres from Earth, that's where Voyager 2 is now. It's now in officially interstellar space. What happens now? How do Parkes and the dishes of the Deep Space Networking camera work together?
So we use our communication dishes to receive data from the instrumentation on board the spacecraft. So Voyager 2 still has 5 instruments operating, and the key ones are the onboard magnetometer, measuring the magnetic field. The particle instruments look at the stream of that energy and the density of that material in the environment where Voyager 2 is, and of course the plasma science experiment, which is being able to detect the inward rushing high energy particles coming from the rest of the galaxy that bombard into our heliosheath boundary, that bubble of magnetic energy that's pulsed out by the sun through the solar wind. So being able to actually get out in front of the wave now, the boundary of our solar system, the sun's initial influence at least, and then to be able to get into the sort of clear air of the rest of the galaxy, that information will continue to be collected and analysed through all the data received through both the Deep Space Tracking Station in Canberra and the Parkes Radio Telescope, which we have use of for the next few months.
Can you use all the dishes at Canberra for that?
Well, one of the reasons we brought in the Parkes Radio Telescope is simply because all the antennas here in Canberra are actually really busy all the time, and particularly in the next couple of months, we have some very key missions coming up. So coming up on New Year's Day, the New Horizons spacecraft will be making its encounter with the most distant object ever visited by a spacecraft, the Kuiper Belt Object 2014 MU69. So we need to actually use our assets on that day particularly to concentrate on that event. And of course, we have new missions on Mars, new missions heading off to the Moon, and another 40 missions spread out across the rest of the solar system. So to maximize the time of getting that information back from Voyager 2, we've engaged the Parkes Radio Telescope to observe it for around about 11 hours a day. We can add in about another 4 hours of time in that tracking. So for 15 hours a day, we can get that valuable data that's streaming back in real time from Voyager 2, which, as I said, would otherwise just be lost to the universe.
That's Glenn Nagel from NASA's Deep Space Communications Complex in Canberra. And this is SpaceTime. I'm Stuart Gary. Virgin Galactic's VSS Unity rocket-powered spaceplane has set a new company altitude record, reaching a height of 82.7 kilometres or 271,326 feet. After being carried aloft to an altitude of 13,100 metres or 43,000 feet below the wings of its jet-powered White Knight 2 mothership, Unity was released, dropping a few metres below the carrier aircraft before igniting its rocket engine and then quickly accelerating up towards the velvet darkness of space, eventually reaching a speed of Mach 2.9 before MECO or main engine cutoff. Unity's two-man crew then experienced a few minutes of microgravity as the spaceplane reached the apex of its ballistic trajectory high above the Californian Mojave Desert. It then began falling back towards the ground, eventually gliding to a perfect runway landing just 15 minutes after taking off from the same runway. This test flight brings Virgin a step closer to its ultimate goal of commercial space tourism. The missions achieved the longest jet in-flight engine burn of Virgin's test program, lasting some 60 seconds. Once fully operational, Unity and other members of Virgin Galactic's Spaceship Two fleet now being built will include up to 6 space tourists paying $250,000 each. But for this test flight, 4 scientific payloads, part of NASA's Flight Opportunities program, were instead included. The payloads examine the effects of microgravity on dust collections, multi-phase flow systems, plant growth, and vibration isolation systems. Virgin boss Richard Branson described the mission as a spaceflight because it surpassed the old 80-kilometre boundary of space formerly recognised by the US Federal Aviation Administration. Of course, the official start of space is actually at 328,000 feet, or 100 kilometres, the Kármán line, defined by theoretical physicist Theodor von Kármán in 1956, and marking the point at which aerodynamic surfaces can no longer control the lift, roll, pitch or yaw of an aircraft, forcing that aircraft to use reaction control systems, such as rockets or jets, to maintain course and manoeuvre. The aircraft has effectively become a spacecraft. Spaceship Two is based on the original Burt-Rutan scale composite Spaceship One design. That's the spaceplane which won the X Prize back in 2004 by becoming the first privately built reusable manned spacecraft to reach 100 kilometres, the official start of space, safely return to Earth, and then repeat the flight within 2 weeks. Branson and Virgin Galactic are building on that with the aim of flying paying passengers on brief suborbital flights, providing stunning views of the curvature of the planet and up to 4 minutes of microgravity. But they aren't alone. Jeff Bezos's Blue Origin company is targeting the same market with his own venture, New Shepard. It's using a conventional vertical launch rocket to fly passengers in a capsule up to 100 kilometres before parachuting back to the ground. New Shepard's now completed 9 successful test flights in 3 years, including 2 which have already passed the 100-kilometre altitude mark. Of course, Virgin Galactic's development suffered a major setback in 2014 when VSS Unity's predecessor, the VSS Enterprise, broke apart in mid-air, killing one of the test pilots after the feathering system used for re-entry was suddenly released during ascent. The feathering system moves the tail booms from a horizontal to a vertical position to help slow down the spacecraft during re-entry. Releasing the feathering system during ascent allowed it to lock into the vertical position, in the process placing a huge dynamic load on the airframe and causing the spacecraft to break apart. Once fully operational, Virgin Galactic's normal Spaceship Two flight profile will see the spaceplane mounted under the central spar wing section of the White Knight II mothership, taking off horizontally on a conventional runway. The twin fuselage 4-engine powered White Knight II would climb to an altitude of 15.5 kilometres or 50,000 feet, at which point it would release Spaceship Two, which would then fire up its single hybrid rocket engine for a 70-second burn, accelerating the spaceplane to a speed of more than 4,000 kilometres an hour, equivalent to over 3 times the speed of sound. Main engine cutoff, or MECO, happens 70 seconds after ignition. The spacecraft then continues to coast on a ballistic trajectory to an apex about 110 kilometres or 361,000 feet above sea level. Passengers to experience 5 minutes of microgravity and spectacular views of the curvature of the Earth from space. As Spaceship Two re-enters the atmosphere, the twin tail booms would be raised to the vertical or feathered position in order to increase drag while at the same time reducing heat from friction to help slow down the rate of descent. At 22.9 kilometres or 70,000 feet, the tail booms will be defeathered again back into a horizontal configuration, allowing the spacecraft to glide to a conventional runway landing. I'm Stuart Gary. You're listening to SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study has found that the widespread drying of soils due to higher evaporation rates caused by global warming is now shrinking water supplies to the point that drought-like conditions may become the norm in many parts of Australia. Researchers with the University of New South Wales undertaking the most complete analysis of rainfall and rivers to date found that for every 1 degree Celsius increase in warming, the warmer atmosphere will be able to store 7% more moisture. The models also expected that this should result in a roughly 7% rise in flooding per degree rise in temperature. However, instead the team's measurements of actual rainflow and river flows indicate that when it comes to frequent floods, those smaller floods essential for refilling dams and water catchments, the reverse is actually happening. It seems frequent floods are decreasing at roughly 10 to 15% for each degree rise in temperature. The team believes this is due to the drying of some soils driven by global warming, which is causing the drier soils to absorb more rain, leaving less to go into water catchments. The findings have grave implications, as they indicate that rivers and reservoirs which are already drying will only worsen as the temperature heats up. A new study has found that young people who identify as LGBTQI are more vulnerable to symptoms of depression from as young as the age of 10. The findings, reported in the Lancet Medical Journal, are based on a survey of more than 5,000 young people, each of whom were interviewed 7 times between the ages of 10 and 21. Scientists found that sexual minority youth were 4 times more likely to report recent self-harm at ages 16 and 21 compared to their heterosexual peers. And there are also far higher risk of depressive symptoms from as young as 10. The good news is that for those who do survive, this effect starts to decline into young adulthood. Researchers think that might be due to increased independence and a change in the people they hang out with. New research into the first complete skeleton of a marsupial lion, which once roamed Australia, is providing paleontologists with extraordinary insights into the species' hunting ability, social traits, and similarities with the iconic Tasmanian devil. A report in the journal PLOS ONE by scientists from Flinders University has examined the skeleton of the lion Thylacoleo caniflex after new remains were discovered, including the only known complete skeleton, in caves in Narracourt and on the Nullarbor Plain. Their research confirms the marsupial lion was a skilled climber, and that the anatomy of the lion is most similar to that of the Tasmanian devil, which nowadays is the largest marsupial carnivore still living in Australia. The first of Australia's next-generation F-35 fighter jets have touched down at their new home at the Williamtown Air Force Base near Newcastle. The stealth fighters have flown direct from Arizona by way of Hawaii and mid-air refuelling. As they arrived, they were accompanied by 4 of the FA-18 Hornets they'll eventually be replacing. Like their FA-18 predecessors, the F-35s will set new technological standards for multi-mission aircraft. But they do come with significant compromises. Firstly, they're not nearly as stealthy as they could be. In fact, with the right wing-mounted forward arrays, new generations of Sukhois and MiGs, the aircraft they'll most likely be going against, will be able to detect them. And although they'll be more reliable than their Russian-built counterparts, they haven't got the speed and manoeuvrability. They also lack the stealthiness and supercruise capabilities of truly great air superiority fighters like the F-22 Raptor, which is now, and probably will remain for some time to come, the world's greatest fighter aircraft. Samsung has finally unveiled its new Galaxy phone with a foldable display screen. The phone, expected to be released early next year, looks like a normal, though slightly thicker, Galaxy 10 smartphone, with one key exception. It folds open, revealing a 7.3-inch double-width screen on the inside, turning the phone into a tablet. The new foldable screen uses Samsung's Infinity Flex display technology to achieve a seamless look. The new phone, which we think is going to be called the Galaxy Fold, will run on Google's Android operating system with a new bubbly look called One UI. Of course, Royal have already launched their FlexiPi foldable phone, and both LG and Huawei are releasing their own versions in the new year, with Apple also looking at the idea. Base model prices for the new Galaxy Fold are expected to be around $1,800 in the US, which means well over $2,000 down under in the land of Oz. With the details, we're joined by Alex Sahara of Reut from IT Wire.
There was actually a company before Samsung's announcement called Royal, and actually I met these people at CES 2018, and they had a bunch of foldable screens that could sort of go down to the dash of a car and be sort of folding and curved in many different ways. But they came out with something that looks like it folded sort of like a book, but it had like a curve on it. Now, that particular device is going to be anywhere from $2,000 to $3,000, but Samsung announced at its developer conference in San Francisco a phone that has that sort of, now the phone itself, what they showed on screen, and people can go to Samsung Infinity Flex foldable phone on YouTube and you can see videos of this. But the phone itself looked quite chunky, and they said, look, we've camouflaged this. The design underneath is much sleeker and better, but we don't want to show all our competitors yet. That's what they're sort of saying. And the phone that Samsung had folded flat. Now, when it unfolded, you had a 7.3-inch screen, and there did not appear to be any joins or any kind of visible indication that the screen in the middle was somehow blemished by this. It looked like a perfectly normal 7.3-inch screen, and you could fold it in half. And on the front of the folded phone, there was a 4.59-inch screen, which a little bit small compared to the fact that we have 5 and 6 and 6.5-inch screens on our mobile phones these days. But even so, the price is meant to be $1,770 US. It's meant to come out in March next year. It's meant to be able to be folded hundreds of thousands of times, and it's the beginning of all those sci-fi movies. So these sorts of things have been around in science fiction for a long time. The initial devices, I guess, basically are still quite primitive compared to what we've seen in science fiction, but they're here at last. last. After being seen sort of as prototypes and demos for CES over the last decade, we're now on stage. We saw this folding phone, and looks as though within 6 months it'll be in stores. It'll be very expensive, but it'll be there.
And that report by Alex Zaharov-Reutt from IT Wire. You're listening to SpaceTime. I'm Stuart Gary, and that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from spacetimewithstuartgary.com, or from your favourite podcast download provider. SpaceTime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more SpaceTime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.